Hi guys, I'm Gouthaman Asokan. I work as a AI researcher in CellStat, and today the topic that we are going to be seeing is text generation strategies. So LLMs have become a very popular space presently, and text generation is one of the areas that helps in creating better text generation with the help of LLMs. We'll be seeing so how this text generation helps in case of LLMs, what is LLM decoding, and we will see what are the different strategies that could be used in creating this generation. So this could be anything from query search. This is the most popular algorithm, and we'll be also seeing beam search, diverse beam search. Then we'll be seeing sampling, multinomial sampling, we will be seeing finally the contrast research and speculative decoding. So these are the different methods in which the decoding in an LLM can be done. So we'll be seeing what are the how the particular algorithm works, what are the advantages and what are its disadvantages in this webinar. So LLM decoding here presently the decoder what it does is it's an auto-regressive language where it creates a text generation. Given a set of sequence of words, it predicts the next word. So this is the basic way in which it works. So here too, if you see, let's take for example the at the time interval t, what is the probability of this word getting generated will depend on what are the other previous words that is getting generated. What is the probability, and it will be conditional probability on those words. So this modifying the decoding strategies. So once we train an LLM, this decoding strategy need not be specified even while training actually. So because this doesn't contain any trainable parameters, this is something that is used only in inference. So we'll be having uh, so we can be seeing what are the different algorithms used, and based on this, how the quality of the output changes. So the main thing why we use this decoding strategies is sometimes the words gets repeated. We will be also seeing examples how the words get repeated. So let's take for example, it doesn't become a big issue in cases in NLP use cases like summarization. But let's take for example, we have a story generation or a poetry generation. So in these cases, what happens is we need something that is very diverse. So in those cases, the repetition must be reduced as much as possible, and here these algorithms will be very helpful. So the first one such algorithm that we'll be seeing is the greedy search. So this is the most popular decoding method that is being used in LLM. So here, how it decodes is essentially it takes the highest probability word given a set of tokens, and in this way it keeps on decoding one such after the other. So that's why it's greedy, because it just sees which has the highest probability and goes on to choose that. So here, if we see this is an example how the greedy search works. So we have the initial token of that. So what are the next probability tokens? We have dog, nice, and car, and each with a probability of 0.4, 0.5, and 0.1. So since nice has the highest probability, after the nice will be the generated output, and after nice, the nice, there are three different probabilities: the nice woman, the nice house, and the nice guy. Each has its own probability: 0.4, 0.3, and 0.3. So again, what we'll be doing is, since it's a greedy search, the highest probability is this one. So the nice woman is what it will get generated if we use the greedy search. So this is the default algorithm that many LLMs use, and even in case if we don't specify any particular strategy, greedy search is the default algorithm that will be taken. So the next decoding strategy is called beam search. So the beam search, what happens is we can be telling how many beams to select, and in these beams. So let's take for example, we can be telling one beam, two beam, three beam. So it will, based on those beams, it will be seeing the probabilities and choose the sequence. So this is different from greedy, because greedy just picks the highest probability. Here we can be telling the beam, and that number of beams that we specify uh, essentially uh, chooses the number of pathways that we can be choosing. So here, in this case, let's take for example that we specify a beam search of two. So the two beams are to be generated. So here, what happens is we have the start token that is being given to the LLM decoder. So once that is being given, there are A, B, C, D, E. These are the different generations that happen, and since we have beam two, so it will take the top two probabilities. So here, if you see, A has a probability of 0.5 and C has a probability of 0.4. These are the topmost probabilities that is being generated. So only these two will be picked. So once we have this, so A and C, so A, C. So with start A, yeah, number of generations will be happening. So here you can see that after A, it is spreading A, B, C, D, E. Again, after C, the decoder will be making as some such as predictions. Here too, it's CA, CB, CC, CD, CE. So here, what happens is we will take this whole thing as a collective unit, and we will be again seeing the beam of two. So that the top two most probabilities. So here, if you see, that becomes AB and AE. So these are the two things. So these two will be getting selected. So AB is getting selected, AE is getting selected. Again, with AB and AE, the whole generations will happen in those the top two. Since the beam is two, that is being taken. So here it will be ABC and AE. So in this way, instead of the greedy search, this beam search helps in uh, getting results that are a little quite diverse compared to that of greedy search. So this is how the beam search works. So that's what is being told in the thing. Unlike the greedy search,
Here, how is the
uh,
probability number calculated?
uh, probability number is the usual the thing like in LLMs, in transformers. How do we create the text generation? So we have the token. The next token, we have a probability for the whole of the vocabulary and the highest we select, right? So in the same way, the beam search also it works the same way. Probabilities for the next token is being predicted, and that in that we select the top two most in each.
I guess in a neural network, it predicts a softmax probability of various output combinations, right?
Yeah, yeah.
So whichever one has the highest probability is picked up. So that way, a machine learning model is always predicting probability of different output classes. So from this, that's when this kind of algorithm kicks in, which one to pick.
Yeah, it's a conditional probability. Yeah, it's a softmax function. It's a conditional probability. So given A, what is the next tokens? So given C, what is the next tokens? So that is it. So this is how the beam search works. Beam search essentially has several hypotheses because we have several pathways that as we can be seeing here, and in that it takes the highest probability for the entire sequence. So instead of each token, like in greedy search, beam search, it takes the overall sequence probability. So that's why this is a little more effective than greedy search. Uh, so the biggest advantage of using beam searches, let's take for example, we need to be creating diverse results. If we take in greedy search, it will always take the high probability token and go in that direction. Here, what it gives it gives a way in which it can even start with low probability. For example, the C, and with C it can go in some way. So there could be a case where it could be C, D, A could be a sequence that could be created. If we had opted for greedy search, that pathway wouldn't have been explored. So this way of exploring the entire sequence helps beam search create diverse results. So beam search is one of the very popular ways in decoding. What the latest papers, what they have done is they have made a little more uh, different strategy, making it even more diverse. So that's the thing called diverse beam search decoding. So it's essentially an extension of the beam search. Uh, what it helps is to create a even more diverse set of sequences. So that is what it is being used. So here, what we need to be telling is, we need to be telling how much groups could be needs to be created. For example, so this is the additional thing in in addition to whatever the parameters that we have used in beam search, which is the number of groups. We need to be specifying how much number of groups to calculate. So here, if you see, there are group 1, group 2, and group 3. So there are three different groups that has been created, and these three different groups could have three different pathways in which it explores the decoding. And each group will have whatever the beam search, the way that we have used in beam search, that works. But in addition to that, there is a penalty parameter. So here, if you see, there is a penalty parameter which accounts for that in that position, whatever the other groups tokens have been predicted. Here, if we see that the token is birds, here if you see the token is the and. So how this token is diverse from these tokens. So this will also be accounted for here. So that is the penalty parameter. So here, if you see the in the group 3, the token to be generated here, what we also keep in mind is it should be very diverse from and the birds, these tokens and the birds. So in this way, what happens is, since we are having different groups and we introduce this parameter of penalty parameter, we will have a very diverse set of generations to pick from. So in this way, the penalty parameter makes the beam search even more diverse. So that is what being explained with formula here. But penalty parameter, essentially what it helps in is to measure the sequence dissimilarity. So how much is the sequence dissimilar, and it encourages for that sequence dissimilarity. So here, if we need to be using the diverse beam search, then parameters that we need to be defining is the number of beams. So how much beams to take, the number of beam groups. So how much groups to take, and the diverse penalty. So diversity penalty. So how much should the weightage be given to the penalty? So here, if you see, uh, this is the formula for the beam search. Here we add the diversity penalty. With that, we calculate the diversity between the generated token and other such tokens in other groups. So this could help in giving how much weightage we need to give for this particular thing. So in this way, we generate the beam search even more diverse with this approach. So this is the third approach that we see. I'll go to the fourth approach if no one else. Okay, so what we have seen up to now is greedy search, beam search. In beam search itself, we had a specific variation called diverse beam search. Now the next sampling idea that we use is the multinomial sampling. So decoding, we make it by sampling. So instead of always going for the highest probability, now what happens is we have a set of tokens. It has a probability distribution. Choosing uh, we'll be choosing by sampling some token from that. So in this way, we select some random tokens from the probability distribution, and this in turn helps in reducing the risk of the repetition. So again and again, when we need to be creating, for example, some different stories, the same set of words won't be used. It will be like different words, and in turn will make the whole text generation even more diverse. So here, if you see the nice house, so what happens is we give the decoder the token of there, and there are some uh, tokens being generated, nice dog and car, and we select through multinomial sampling one particular token. So here it's just taking nice, and there nice it's been taken, and we generate a set of tokens. In that, again, the sampling is done. So here, if you see in the previous approaches, most likely the woman is the next token that would be picked up. So since it's a multinomial sampling, we would be taking any token from these sample space. So here, even though house has a probability of just 0.2, that is being taken. So it will be the nice house. So that is the generated sequence for this particular example.
Gouthaman,
Yeah,
question. So you said like it does a random sample, right?
yeah.
Uh, Wanted pick up stop word or something like that, some like low probability word. So is there any threshold or something which is deciding that?
Yeah. So multinomial sampling in general would mean that it could take from any token, but we'll be seeing in the upcoming slides. So here too, there is a threshold with which we'll be selecting.
Yeah. Okay. Cool.
So multinomial sampling is essentially sampling from the whole set of the vocabulary. But that again would make it more incoherent, and the sequence wouldn't have any meaning at all. So we just need to have a trade-off between the diversity and making the sentence coherent. So one of the ways that could be achieved is top case sampling. So top case sampling is essentially that we choose the number of the top uh, K tokens that would be used for choosing our next predicted token. So here, let's take for example, uh, a top K to be 6. So here, if we see, given the token D, what is the next word likely to be present? So here, because we have taken only 6, 1, 2, 3, 4, 5, 6. Only these words would be taken for the sampling, and the people, big house, car, these won't be taken for the sampling. So that is the top case sampling. So again, if you see here, the probability of the word given the sequence, the and car. So again, here if we see, drives, his, turns, stops, down, yeah. So these 6 sequences will be taken for the sampling, and not the small toll. So these won't be taken. So we take only the top six for selecting our decoding strategy. So this is in this way we can be making it more coherent also, and at the same time we can be making it the generated sequence to be diverse. So that's how it works. But one of the issues with using the top case sampling is uh, it could work well with so the distributions would not always be very sharp, very distinct words. So here, if we see, there is some very big distinctions between each of the words. But here, if we see, let's take for example, we Leo the first thing, others are more or less the same. The distribution is even more flatter. So in those cases, if we take the top 6 or something, it could not adapt well. So we need a sampling strategy that dynamically takes the number of tokens instead of that um, instead of the hyperparameter that we use. So in that way, we can be making even more effective and effective predictions. So what is the upgrade they made is the top P nucleus sampling. So here what happens is we take the top P, essentially the probability. We have a probability threshold, and in that within that threshold, whatever the tokens comes, we take. So this can be for the next sequence some 10 uh, tokens. So 10 tokens could have a probability more than the threshold. Again, the next sequence could have a 20 tokens more than the uh, probability threshold. In this way, we dynamically choose the tokens based on this probability. So this helps and works a lot more better than the top K predictions. And how we use here is here if you see the threshold that is being given is 0.92. So any token that is above 0.92 is being taken for the probability. So here if we see I star car woman guy. So anything the blue colors we see all have a probability more than 0.92 except cat. I think everything has a probability. So we take all of these tokens and do a sampling with them. Here too, what we see is 0.92 we take. So here if you see, only the first three tokens comes more than 0.92. So only we use these three tokens for the sampling. So in this way, dynamically we select the number of tokens in which we can be selecting from. So that's how top T, which is the nucleus sampling works. So those are the main things, and we'll be seeing the next is the contrastive search. So contrastive search is again one of the ways in which we can be getting diverse examples. So here, if we see, so how do we obtain a contrastive searches? Uh, we give a weightage to the model confidence. So what is the rated word? For that, we give a weightage, and we subtract that from the degeneration penalty. So how similar is this token compared to the tokens that have come previously? For example, let's take for example, there are some 5 words and the 6th word we need to be predicting. So what happens is, what is the model confidence? What is the probability for the 6th word? So that happens to be this model confidence. And the degeneration penalty is essentially for that 6th token, how different that is from the first 5 tokens. So that we use to create this degeneration penalty. Let's take for example that the 6th word, there is 2 things. One has a 0.9 probability, one has a probability of 0.8. The 0.9, even though it has model confidence, if it is something that is very similar to the previous words, it will have a higher penalty, and in this way the subtracted thing could something be, let's take for example 0.6. So the 0.9 after getting subtracted it will become 0.6, but the 0.8 could be something very diverse, and it could after subtraction it could be 0.7. So the net value would be more favorable for the second prediction, and in this way that would get as the token to be picked. So in this way, the contrastive search helps in looking for words that is in something that is very contrast to the previous tokens that has been predicted.
So this is to avoid the repetition of words or repetition.
Yeah, the repetition of words. So all of these the techniques essentially it helps in making the results more diverse. Instead of let's take for example, we give a the LLM to predict a big paragraph. When we use a greedy search or something, what happens is it will be telling the same point in different ways. There will be repetitions. So when we use these kind of algorithms, it will make it very diverse. So again, we see it through visualization to how the contrastive searches are different. So here, if you see, without the contrastive search, when we use a greedy search, the tokens that is being generated, they are finding the similarity, something like a cosine similarity. And here, if we see these sequences and these sequences, so all these sequences have very big similarity. That's why here, if you see, it's very dark blue in color. But here, if you see it just the similarity only happens in the diagonal space, which means that it's very diverse. But in the greedy search, what happens is even some of the paragraph, the different lines are very similar and it's getting repetitive. So that's the thing that they show with visualization. So so that's what the model degeneration. The generated text becomes very unnatural, and also case has that repetitions that we want to avoid. So that happens with contrast research, which we can't be uh, achieving through greedy search. So the last method that we'll be seeing is the speculative decoding. So what happens with speculative decoding is essentially something like that of knowledge distillation, where we have a teacher student model and both learns from each other. So here too, it has a assisted decoding. So what happens is there is an assistant model. Uh, so this assistant model will generate a few tokens, candidate tokens, and the main model function is just to pick whether that token that it's giving is correct or not. So this way, to choose the token, it takes a lot of time. When we decouple them and make it as an assistant model, these tokens to be picked, that takes significantly lesser time, in which in turn speeds up the decoding process. So that's how uh, it is done. An example here, if we see, so so here if we see, this is LLM text generation that is happening. The green colors are the text predictions given by the smaller model. So here if we see GPT like transformer decoder with 6 million parameters. Uh, so that is the assistant model. The main model is the 97 million parameter model. So that is the model which tells whether it's correct or not. So it's telling. So here, if you see the red color, those are the things it's rejecting. The assistant model is predicting some words. The bigger model, kind of the parent model, uh, sees whether we could keep it or not. So here, it gives the Japan's benchmark it's taking. When it gives that assistant is giving the token bond, it's rejecting. It's taking the next other things. The n. So it corrects instead of bond, it gives the parameter n. So it also has the capacity to right. So once we have Japan's benchmark n, it again the assistant model gives. So in this way, the assistant and the parent model uh, gives back and forth to create the whole generation. So this is the speculative decoding. So this is also one of the ways in which we could be decoding the text generation. So these are the different ways in which we can decode, and based on our use case, the uh, decoding strategy will be different. So yeah, these are the things. I will also show some examples over this. So here we are using with Hugging Face. We are initializing a model. So here what we are initializing is Distilbert. So Distil GPT-2. So that is a checkpoint. And here if we see, we try to every method how the generation comes. So here we first what we use is the greedy search. Greedy search we give the prompt that I look forward to. So the model to be used is the Distil GPT-2. So we initialize the tokenizer. We give the inputs, we initialize the model, we generate the outputs. So the inputs is the I look forward to. The outputs is the what is the next set of sentences. So For greedy search, we don't need to give any extra parameter. So as such, it will decode and give. So I look forward to the thing, seeing you all again, and it gives this. So in this way, greedy search essentially takes what is the highest probability, and in that, it's giving this thing. Yeah. The next thing is here. If we see the top K we are using maximum number of tokens to be generated and maximum number of new tokens to be generated. What is the top K? So only the first top four to be used, and we also use the diverse search. So that's a penalty parameter. So that is also been specified, and we decode the tokens. So here, if we see. Uh, this is how the Hugging Face. So with Hugging Face, is Hugging Face company is the initial token that is being given. So this is the final token that is being generated. So it's a family-owned and operated business. We pride ourselves on being the best in the business and customer service. Second to none. If you have any questions or on products, feel free to contact. So this is how it's getting generated with the diverse search. Uh, in greedy search, what happens is uh, we have been around 30 years. It's the best quality. We are a family-owned business. So here, if you see, we have been providing, and we are proud of the community. We are again proud to be part of the community we serve. We are family-owned and operated business. So if you see here, it's already established that it's a family-owned and operated business before. It's again telling this, and again it's telling it. We are proud of the part of the community. In this way, the repetition happens when we pick the greedy search. But when with diverse search, what happens is it makes the uh, generation even more distinctive. So again, here if you see, we use the OpenAI community GPT to batch. Here, what we do is we use the beam search and we use the sampling. Number of beams is one. So this is the general thing. Do sampling. So what it does is it gives a multinomial sampling. So today was an amazing day because this is the initial token that is being given. So each of these generated things, we received these wonderful items by the way of a gift shop. The box arrived on a Thursday, and I opened it on Monday afternoon. So these
Sorry,
all these things.
There are questions actually.
Yeah.
Yeah, please use.
Yeah, so it's doubt regarding top K sampling technique. So when we calculate the top K words, so is it depends on the input that is given in the prompt, or it is independent of that?
It depends on the prompt. So it's a conditional probability. So whatever input that we have given, for that, essentially the transformer gives a probability distribution for all the tokens. So in that, what is the top, for example, the top K, let's take for example, the K to be 5. So what is the top 5 tokens for that?
Okay, okay. And is there any guideline around like how to select this number?
Uh, it's a hyper parameter actually. So there is no as such any specific optimal number. So we need to be testing out and finding the thing that is needed for our use case.
Okay. Thank you.
Guys, you can unmute and ask the question.
Yeah, one question, like which method in this program, like how you are saying it is a greedy algorithm?
Yeah, the Hugging Face, what it gives us, if we don't specify any such thing. So here, if you see, we don't specify any extra parameters. We just initialize the model and generate. So as such, it's greedy search because it's a default search that it has initialized. So when we give extra parameters, then it tries for the other search.
Then when you're passing the parameter, then which algorithm is following?
The first one, it's a default greedy search. So let's take, for example, the diverse search. So here, if you see the model generate, previously I have just given the inputs. Now I'm giving the parameters, penalty alpha, the top K. So in this way, so here we need to be specifying the parameters for which search that we.
Got it.
Yeah, there is a question called what is seed here?
What is?
Seed.
Uh, where is the seed? There is the seed here. Probably seed is just to uh, make the generation little uniform. That's it. For reproduce. That's what. Just for like the random number, we have the seed. Just like that. Yeah. These are the things.
What are these special tokens? Skip special tokens.
Where is the special token?
The tokenizer.batch decode using skip special tokens. Yeah.
If special tokens, I'm not sure what it is. Probably the special characters to skip those, not tokens. This is the thing I will also show here. So here, if you see the number of beams, the previous time it was 1. Here we are keeping the number of beams multiple 5. So when we keep 1 and do the sampling, it's a multinomial sampling. Here when we do the number of beams higher 5, it's a beam search. So here the sequence is getting generated with beam search. Yeah, here too it's a beam search thing. Here what we do is diverse beam search, where we specify the number of beams, number of beam groups, and the diversity penalty. So when we use specify those parameters, it automatically picks that as diverse beam search. Yeah, here it's the speculative decoding, where we use the assistant model. We specify what is the model here, what is the assistant model, the checkpoint for all these things. So here the parent model has 1.4 billion parameters. This has 160 million parameters. And with this too, we decode the thing. So that's how the output is being decoded. So this is speculative decoding. And again, this is speculative decoding, where we use the assistant model and we use the model to decode it.
So Gouthaman, how is this speculative used? I mean, where is it? Where is the use case of it? It uses two models, if I'm not wrong. But
Yeah. So it's just a different way in which we can decode a thing. Uh, so
okay.
Yeah, why this being used is like uh, mainly for the inference. It will have a lot more less inference because the smaller model generates the new tokens and the larger models work is just to pick which token from that.
So in this way, like compute power is reduced, or
Yeah, computational is
okay. So it's similar to that generator discriminator concept. It works as a
yeah, something like this, even like the knowledge distribution. Yeah, these are the things I wanted to discuss. If you guys have any other doubt.
So in final, this is basically it's a revolution, right? Like one after the other. What is widely used, and is there any multiple methods which are used in combination or something in future models or current models, latest models?
Okay, I searched for ChatGPT. It's not very clear how they are using. So they haven't, I think, explicitly mentioned that. Only thing is it is use the sampling. So it's used the top case sampling for the generation, and it's not like there are different algorithms because not everything fits for every use case. For example, this summarization, we don't is essentially a summary, so it will be a one or two sentences, and we don't need much of any diversity in that. So there we can be using greedy search. But when we want to create a story, a long story kind of thing, there the repetition needs to be reduced. So in those cases, something like a diverse search would help.
Okay, any other questions, audience?
Yeah, I think it's done. Yeah.
Okay, so thank you all for joining. Thanks, Gouthaman. Nice presentation. As I was saying, we have a course coming up, so do enroll. If you have any other questions for Self-Strat, do contact us. Our contact details are on our Meetup page. Thank you, Gouthaman. Thanks, audience. Have a good Saturday evening. We'll see you tomorrow again in our next set of webinars.
Yeah, also just to add, please fill the survey which is floated in the chat box. That would be very valuable for us to record your feedback.